Okay, so welcome to, wow, lecture 23. Maybe you'll have to put up with that, because I don't know how to control the volume. Is that too loud? No? All right. Sounds funny to me is what it does, but anyway. Welcome to lecture 23. This is going to sort of finish off our example small signal circuit analysis and then get to high frequency small signal models, and that's probably where we'll finish up today. So we'll finish up that common emitter example, and then we'll try to start frequency response again, but as far as we'll get is the high frequency model for the BJT. Yeah, I really don't see the sound control on this. All right, anyway. I guess, just some announcements. Homework number 7, that's due this Friday. Lab number 5 is going to be due quite a while from now, so Tuesday, November 12th at 5 p.m. You will definitely know that deadline very well, because when you get down there, that's when you're going to, if you haven't finished your design at that point or written up your project, that's the part in this class that gets a little bit tough, because you have to manage your time with this, and you don't want to be writing up the report for that first project on that last day before Tuesday, right? So you want to get done with this stuff at least a week in advance. Give yourself a week to do that report. I passed out the exams already and gave the Z-scores last time. I don't have any of the straggler exams with me right now, so if you want your exam, I guess follow me back to my office today, and you can get it, or show up in office hours whenever you can, and you can get it. But you can also watch the last lecture or two to get details on performance and on the solutions for the exam. I also have the solutions to the exam in my office. Okay, any logistical questions on anything? Okay. So last time we were going through this common emitter amplifier example, like I said, and this was it. So we're sort of solving this circuit. And when we solve a circuit using small signal analysis, we're dividing it into two circuits basically. We're dividing it into a large signal circuit and a small signal circuit. So the large signal circuit will give us the solution to this. The small signal circuit will give us the solution to this, which is a small AC signal. And then the actual signal is going to be the superposition of these two, so we'll just add these two together. Okay? And last time we started doing this, we determined the DC operating point. I taught you how to get the DC circuit. That basically means open circuiting all large capacitors, turning off all of the small signal AC sources, and then solving the circuit. We did that. The next step in this is to actually do the small signal analysis, which requires us to create the small signal model. So we actually use the DC bias operating point for the transistor to determine its small signal elements, which are GM, R pi, R naught, and if we want, we can derive the RE. And then actually draw the small signal circuit, which is a different circuit than the DC circuit, because what you do in this circuit is you short the capacitors and you zero out any DC sources. So you can see the VCC voltage that used to be up here, I've grounded. And this capacitor that used to be right here, I shorted, which removes that resistor in the small signal circuit. So the small signal circuit and the large signal DC circuits are different circuits. That's the main takeaway from this, and you should know how to create each of those. We then analyze this circuit, and the way that we're doing it, at least right now, is to replace the transistor Q1 in there with its small signal equivalent circuit. And so this is the small signal equivalent circuit for a bipolar junction transistor. The VBE, R pi, this voltage controlled current source, and this output resistance R naught. These resistors are part of the bias path R1 and R2. The dotted line here is just telling me which is the amplifier versus which is the source and which is the load. Okay, I guess I should go back and actually put a dotted line around this too, so I can show you what corresponds to what. So if I were to pull out the amplifier, well, that's the source there. So the amplifier is going to start from the source resistance on. Right, this is going to be more of the amplifier, and I'm going to go all the way out to before that resistor RL. So in the dotted box is the actual amplifier that includes the R1, R2, RC, and RE associated with biasing up that transistor. This RL is the load that we're trying to drive. This RS and that VS is the Thevenin equivalent for the source that's driving this. And what can be driving this can be all sorts of things. It can be a microphone, it could be another circuit like this, and it's going to have its own source resistance and its own AC source voltage. And again, I'm saying the AC voltage is the one that's important here because in most information, the important voltage is the AC voltage, the time varying one. Like my voice that you're listening to right now, that has a lot of frequency components, it's a time varying voltage. Okay, and so we went ahead, and before we actually solved this circuit, which you solve using the same generic circuit analysis techniques that you already know, so Kirchhoff's current law, Kirchhoff's voltage law, what I call KCL and KVL. But before doing that, we sort of wanted to equate this thing to something similar to what we were using for op-amps. So remember, with op-amps, we were worried about the input resistance, we were worried about the output resistance, we were worried about the gain of the op-amp. So this is just like that op-amp circuit here, except in this case we don't have a differential input. And what this tells us is that the gain of this is the same as the gain that we had for the op-amp circuit. It depends on what the input resistance is to the amplifier. It depends on what the output resistance is. And so the gain is not just this A sub V. It's preceded by a voltage divider between RI and RS, and it's also modified by the voltage divider between the load resistance RL and the output resistance. So if I wanted to define this amplifier and know how it really performed in an actual circuit, at a minimum, I need to get this RI, I need to get this AV, and I need to get this R0. Okay, so I need these to describe the amplifier. Because they, in the end, tell me what my ultimate gain is going to be, what that total gain, A total, is. Okay? And so we went about starting to do this, and this is saying all the same things, what we need there. But we went about first getting the amplifier gain, and I guess on this side I should just go back to this one right here. Okay, so to get that amplifier gain, we solve this circuit up at the top. And the way that we're doing that is we're saying that we want that amplifier gain when the amplifier is all by its lonesome. So we're going to take that RL resistance and send it to infinity in order to get that amplifier gain. If we just want this A sub V, okay? And so we're basically solving for V out, which is the voltage at this output node, divided by V1, which is the voltage at this node. And notice I'm taking the voltage there instead of Vs because Vs and V1 are not the same. But if I just want the amplifier gain, I've got to take the voltage right at the input to the amplifier, not from the source. Because the source to V1 is modified by that voltage divider between all this resistance and that resistance RS. Okay, so to get that gain, I basically just solve this circuit. And in solving this circuit, all that's going to happen is this V1 is going to be across this R pi. V1 is going to be equal to VBE. And so this current that I'm driving through this voltage controlled current source is going to be GM1 times V1. Okay, and that current then is going to go through this R0 and this RC, where R0 and RC are both going to ground. So if I'm taking current, I'm shoving it up a resistor from ground. What that's going to do is create a negative voltage out there. That's why I've got this minus sign here. So this becomes minus that current GM times V1 times the total resistance I see to ground from that output node, which is the parallel combination of R0 and RC. And this then gives me the total gain. If I then divide both sides by V1, I get V0 over V1 on this side, and then I get the gain on that side, which ends up just being minus GM times R0 in parallel with RC. I went on to say that because R0 is generally much larger than RC, right, we talked about how RC was only equal to about 3 kilo ohms. So let me write some of that down there. So the R3 should have been red. So that RC is 3 kilo ohms. The R naught we calculated as 100 kilo ohms. Okay, so obviously the R naught is a lot greater than RC. And so as far as I'm concerned, the R naught is not there, right? Parallel resistor combinations, it's the smaller one that wins when it's a lot smaller than the bigger one. And so RC is a lot smaller than R naught. And so I'm just going to say the gain is equal to minus GM times RC. And if I plug in my value for GM that I showed previously times that RC, I get a gain of minus 120. Okay? Now, the other interesting thing to do, this is the actual gain of this circuit, but we should ponder what is the maximum gain that this circuit can give us. So say we had complete freedom of design. We can choose the R's to be anything we want to. What is the maximum gain? Well, the maximum gain then will occur when RC goes to infinity, right? So I can write that my maximum gain occurs when RC equals infinity. But remember, my gain, I can't just use this equation for RC. My actual equation then boils down to this one here. So that means that the maximum gain happens when the RC is much greater than R naught in this equation here, where I'm pointing on the left side. Right? So the maximum gain then turns out to be equal to minus GM times that R naught. And if I plug in the equations for these, that means that becomes minus the DC collector current divided by the thermal voltage VT times the formula for R naught, which is the early voltage, V sub A, divided by that DC collector current. And so you can see that those collector currents cancel out in this, and this ends up being minus VA over VT. Okay, so that's kind of an interesting thing here. That means the maximum gain, if you could send R sub C to infinity, ends up being dependent not on your circuit at all, not on the R's that you put around your transistor at all, but on the physics, on what the early voltage is divided by the thermal voltage. That's the best you can get out of this transistor. Okay? Always a good thing to do, to figure out what your maximum is. All right, so we have part of this problem done. So remember what I said. We need to specify this amplifier, not only this gain term, but also, was that a question, or anyone have a question? Yeah. Oh, no. Okay. We not only need this gain term, but we need the input resistance and we need the output resistance. So we have to go about getting that input resistance, and this is something you know how to do already because you already got some practice doing this on op-amps earlier in this course. Except instead of doing this on an op-amp, we're doing this on this small signal transistor circuit. So to get that input resistance, I'm going to need to draw my circuit again. And so I want to draw out my small signal circuit, and sooner or later you'll get used to drawing these circuits. So I'm going to have my R pi. Across that I have what I'm calling VBE. I'm going to have a voltage controlled current source that's going to go as GM times that VBE. Across this I'm going to have a output resistance R naught. And then around this whole thing, for biasing, I'm going to have my RC resistance. This is going to ground in the small signal circuit. At the input, I'm going to have a resistor here, R1, in parallel with R2, which is part of that bias string there. And so this is where I want that RI. So if I go back here, go back up. See where RI is right here? I'm looking for that RI. And so that's basically the RI that I'm seeing looking in this way into the circuit. Doesn't include RS. It's in from this dotted line into the circuit. Okay, so I'm applying my test voltage right here. Okay, I'll call my test voltage Vx, and I want to measure my test current Ix in order to get this input resistance. So see, it's exactly the same procedure that you were using to get the input resistance of op-amp circuits. Nothing's changing there. We open circuit the output like we do in all cases, right? So that makes this current equal to 0 coming there. if that current is equal to 0, then I'm not really worried about R0 and RC. I'm not worried about anything on this output section here. I'm worried only about what's on the input here. And here I can just look in and see that my input resistance, which is equal to this V test voltage divided by the test current, that's just equal to any resistance that I see looking this way into that ground. Okay? And so what is that resistance looking in the ground? Well, that R pi is going to ground. That R1 and R2 are both going to ground. So basically what I have is R pi in parallel with R1 in parallel with R2, and this now becomes my input resistance. Okay? And so that's the input resistance of this circuit here, and that, if you plugged in numbers, would be equal to 1,875 ohms. Okay? Any questions about what I just did to get the input resistance of this circuit, of the amplifier? Okay, so we can move on now to get the output resistance. Again, this is the same procedure that we were using when we were doing this for op-amp circuits. So I'm going to draw up my circuit, and as you watch me draw this, hopefully you'll notice that drawing this is kind of tiresome. Right? It takes me time to draw this. I would rather not draw this all the time, and soon I won't be, in order to streamline the way that we actually analyze these circuits. So we're analyzing this circuit right now where I'm drawing everything for you, because I'm trying to teach you how this is all working. It's always good to do this at least once or twice or 3 times. But when we start getting to other circuits, we will never draw this again. Okay? But when you see a new circuit, you should always draw this. And so I am drawing this right now. But it is taking me time. And so to get the output resistance, of course, I'm going to apply my test voltage source and measure my test current going into the output terminal. But I'm going to do that as you've done before. Okay, so I'm still going to have this R1 and R2 in parallel with the input. I'm going to do that with the input grounded, right? Just the same way that we did when we were doing op-amp circuits. And of course the emitter in this circuit is also grounded there. Okay, so if I have something like this, if I have grounded the input and I have ground there, that means VBE is equal to 0 volts, right? If VBE is equal to 0 volts, then this thing, whoops, that should be a current source. I don't know why I drew a voltage source there. It's a current source. Then this current source goes away, right? I get 0 current flowing through that GM-VBE. Okay, so in that case, I'm basically not worried about anything that happens at the input, because if I've got 0 volts across R pi, that also means that any current here going through R pi has got to be equal to 0. So any current contribution from here is nothing. The only current contribution I'm going to get is from this Vx across the R0 and the RC in this case. And so in the end, I can just look at this and see that Vx over Ix, which is going to be equal to R0, is just going to be equal to the parallel combination of R0 and RC. Okay? And like I said before, this is basically just equal to RC for the case where R0 is much greater than RC. Right? So in the end, this is the equation that I can write for R0. And that, if you plug in the numbers, well, the only number to plug in is RC, and that was given us 3 kilo ohms. Okay, so now we have completely specified our amplifier. We know the input resistance, which is this. We know the output resistance, which is this. And we know the gain, which I had on a previous slide. And so now what we want to do is get the total gain for this circuit. And so let's go ahead and do that. So here for the total circuit, the gain is just going to be V0 over Vs. So I'm trying to go all the way from the actual input signal that I applied to this, so from that Vs all the way to the V0 here. Actually, it's better to do it. Oops. That's not good. Okay, from here. So I want to go all the way from Vs to V0 here in the small signal. I'm still in the small signal domain, but I want that entire gain. And so what that gain is equal to is going to be the gain from here to here, from there to there, and then from there to there. Okay? And so this is just going to be equal to the gain of this first portion here, which is basically just a voltage divider between Rs and the input resistance of my amplifier. Actually, the better circuit to use is this, right? So it's going to be this gain, Ri over Ri plus Rs, times that A sub V gain, that's of the amplifier, times this RL over RL plus my output resistance, which is R0. Okay, and now I can plug in these values for all these things. So I could say this is then equal to my input resistance I derived as R pi in parallel with R1, parallel with R2. So that's going to be divided by another R pi, parallel R1, parallel R2, but then plus Rs. Okay, the voltage gain A sub V I derived as minus GM times RC. And the output resistance I derived as just RC, so I can write this as RL over RL plus RC down there. But now I can take a look at this, right? I can see that, you know, if I join these two together, the RC and the RL over RL plus RC, you can recognize that this is just equal to the parallel combination of RC and RL. So that means I can rewrite this whole thing, the gain as just being equal to, and moving the minus sign to the front now. Still this R pi parallel with R1, parallel R2 over R pi, parallel R1, parallel R2 plus RS times GM, but now times that parallel combination of RC and RL. So that's my equation for the total gain from Vs to V0. I can plug in my numbers that I was giving along the way. And so this becomes minus 1875 divided by 1875 plus my source resistance, which I gave as 100 when we started this problem, times GM, which we calculated as 0.04, times the output resistances in parallel, well, times RC and RL in parallel. So that would be 3 kilo ohms in parallel with 15 kilo ohms. And if we then calculate all this, this ends up being minus 71.2. And that then ends up being my V0 over Vs in the midband. So that's my midband gain. So that's excluding the effects of roll-off due to capacitors that we'll talk about a little later on. Okay, so that's the total gain of this. And so, you know, you can use this same technique to get the gain from any point to any point on this amplifier. So right now we're talking about the gain from the input to the output because that's usually what we care about. But I can also say just for kicks when we do this. So just for kicks, let's get the short circuit current gain. For this common emitter amp that we're looking at. Okay? And so basically for the circuit in the box. Where the box is this box on the right side there. Okay, so say I wanted that short circuit current gain. So I can define that. At least one definition for that could be AIS for the current gain short circuited. with the output short-circuited. That's going to be the I0, the output current, divided by the input current with the load equal to 0, which means the output is short-circuited, right? Or I could say that V0 is equal to 0 here. I'm just shorting the V0 in this case. And I'm really looking at the same amplifier, except my input is now a current, and my output is now a current. And I guess I'll take the current from the output going in that direction. If I took it going out, then I'd take my answer and put a negative sign in front of it. Okay, and so in order to analyze this, I'm going to want to use an equivalent circuit again. So I'm going to have to take my equivalent circuit, which is this same small signal equivalent circuit. So I'm going to draw it yet again here. That's GM times VBE. So I'm trying to do this enough times that you get used to it and you kind of get bored of it to some extent, because you'll initially will be drawing this thing, but at some point you'll get sick of it and you're going to want to do this without drawing this. And so hopefully you get, I want you to get to that point basically. And out here I have this resistor, R1 parallel R2. And so in this case, I'm going to shove in a current. There's my II. I'm going to ground out my output. And I want to measure the output current going into that ground. In this case, going out of that ground, because I'm taking that as my polarity for this. Okay, so how do I go about analyzing this? Well, my output current, I0, with RL equal to 0, which is what this is, that, looking at this, is going to be all the current that's coming from this GM right here. Right? I've short-circuited my output. This is still a short here. Right? So I have 0 volts across these two resistors. If I have 0 volts across those two resistors, then they're basically not there. Right? Because they have 0 volts across them. Right? 0 AC volts. So all I have is this current source that's generating that output current. So let me go back here. And that's just going to be equal to GM times whatever VBE is. Okay, at the input, I'm shoving a current into there. And that current is going through that resistor to ground. It's also going through R1 and R2 to ground. So this resistor R pi and R1 and R2 are creating VBE. So basically I could say that VBE is equal to that input current times the parallel combination of all those resistors. So that's going to be R pi parallel with R1 and R2. Okay, and so now combining these two together, I can write I0 with RL equal to 0 is just equal to GM times R pi parallel with R1 parallel with R2 times II. Okay, which tells me that I can then write my gain, AIS. I'm trying to fit everything onto this page, obviously, because I got something on the next page. That's why I'm squeezing it into this here. But this AIS then is that GM times R pi parallel with R1 parallel with R2, which is, you can see, equal to just GM times RI. Okay? And so that's my answer to this, but getting to this answer is interesting, but even more interesting is, what if I took R1 and R2 equal to infinity? Okay, what if I did that? If I did that, then my current gain, if you look at the equation, is just going to be equal to GM times R pi. And remember the equation for R pi? What's R pi equal to? Beta over GM, right? So this thing ends up just being equal to beta. Okay, which is kind of cool. That says that the maximum current gain that I can get out of this transistor is beta, which makes sense, because the beta is the current gain of the transistor itself. Okay? So that's how you work with these small signal circuits. It's no different than circuit analysis per se, using Kirchhoff's current law, Kirchhoff's voltage law. You just have some new parameters, some new circuits to play around with. And that's all I'm doing. I'm just solving these circuits there. And it's a lot of work the way that I'm doing it right now. right? So I've basically done a small signal analysis for you, and it took me 2 lectures to do this. Right? And I'm telling you that in the future, I want you to do this in a minute on your exam. Okay, so how will we get to that point? And so we'll talk about that, but I guess first let's talk a little bit more about what exactly we did. Okay, so back to this, right? This was the original problem we were looking at. It was this transistor circuit here, and we knew that the input we were applying was 1 volt DC and an AC voltage with an amplitude of 0.01 volts. It's going to be at some frequency that's in the mid-band range of this, and the total signal there is just the sum of those 2 signals. Okay, what I'm interested now is, and why I did all of that work, is I want to know what the voltage is right here. What is that voltage? Okay, if I want to know that voltage, then let's go to the next page. And I guess I've already sort of written this out for you too. There it is. Okay, to get that voltage, I know that that voltage is going to be the combination of a DC value plus that AC value. We determined that DC value to be 9 volts. So if you remember from previous parts of this lecture, right here. Okay, we did this DC analysis using the DC circuit. The collector voltage ended up being 9 volts. Okay, and so let me go back to that page I was on right here. And so there's my 9 volts. Okay, we then did the small signal analysis, and we had to determine what this voltage looked like. I'm already drawing it there, but to determine that, I have to determine the small signal VC. So little VC, that's equal to the source voltage, which remember was 0.014 volts times the cosine omega t. And I'm multiplying that now by the gain, V naught over Vs, that we just calculated. That's minus 71.2. Multiply these 2 together, I get minus 1 volts. Okay, obviously I designed this problem to come to 1 volt, right? So that's minus 1 volt times cosine omega t. So where the input was a cosine, the output is a minus cosine, which I'm drawing right here. It has a 1 volt amplitude, right? So it actually is not that small a signal. The input definitely was a small signal. 14 millivolts is a small signal. But the output, definitely not a small signal. But still, this analysis works, and I'll tell you why in just a second. But the total voltage then at this node that I'm pointing at is going to be a 1 volt oscillation around 9 volts, as is shown right there. Okay, so that's what I just did. I got my total input signal right there, which is this. I got to my total output signal, but I did it by splitting the problem into 2 problems. 1, a DC problem where I had to handle nonlinearities. 2, a small signal problem where I got rid of the nonlinearities using Taylor series expansion, and where I assumed that at least the input signal was very small. And that's what allowed me to use the Taylor series expansion to simplify this. Okay? If you take nothing else away from this class, take that away. Okay, this is a very powerful technique that's used again and again and again. We're using it now for transistors. I use it in research for mechanical devices where we're actually modeling mechanical devices. People use it in mechanical engineering, fluidic problems, everything that is solved. A lot of things that are solved, the reason why we were able to solve them is we could take the nonlinear problem and linearize it by assuming small signals. Okay? Again and again you see this. So this is probably the most fundamental thing that you will learn in this class. And you'll see later on just how powerful this is going to be. Because, right, this may have looked bad, but believe me, by the end of this, you'll be flying through this. This will be a very simple problem to you later on in this course. Okay, but before we talk about, doing this faster, and we actually won't talk about that until a couple of lectures, because I have to also talk about the frequency performance of this, which is going to come next. But let's take a step back and let's ask ourselves what was happening from a device perspective here. Okay, so we did all of this in terms of, okay, here's my small signal circuit. We knew the Taylor series expansion. We looked at the math and why the math worked, basically. But from a device perspective, what's happening? So with a device perspective, what you're looking at are its IV curves. So current to voltage curves for this device. And so what exactly did we do when we're making this amplifier work. So there's my transistor there, and so these are IV characteristics for the transistor. This is IC versus VCE, right? That's the characteristic right there. And what I'm basically doing is we've done this before. I'm taking the transfer characteristic from my active device, the transistor, and putting it together with the load line made by my load device, which in this case, it actually for the real amplifier was RC in parallel with the RL, but to simplify things, I'm just saying it's RC right now. Okay? And so I put that load line right there, and then this is a plot of IC versus VBE. Right? This is sort of like a diode plot, because the input to a bipolar transistor looks like a diode, right? You're going from the base to the emitter, and that looks like a diode that you're turning on. So that's why that looks like a diode turning on. Okay? But what did we really do to this? What we did was we biased this device. Right? We biased it at a very specific current. And so just looking at this device, across here, I'm going to get my total signal VCE. So that's a little v, capital CE. Right? I have a current that's flowing through this device, which I could say is a total current, which I'll call IC, so there's a capital C, is equal to my DC current IC, capital C, plus my small signal AC current, little ic. Okay, across here I have little v, capital BE, to be my total VBE, and that we know is equal to my large signal DC VBE plus my small signal sinusoid. Right, so this thing right here is an AC sinusoid. Okay, and so with this, let me now put those things on these plots. So you can sort of see visually, at least from the IV characteristic, IV curves, which sort of describes the physics, what's happening in this whole thing. Okay, so first I'm biasing up this transistor with DC bias current I sub C. Okay, and so let me take an I sub C. Let's take this point right here. Project across there. That's my DC bias point, capital I, capital C. Okay? And I got that because I set my VBE, my capital VBE, to be some value, which is that value right there. Okay? So that is my bias point right there for this whole thing. And so what do I do in this? I'm going to wiggle VBE, right? I put an input signal into this, and that input signal is essentially just wiggling VBE. Okay, and I'm going to wiggle VBE within a certain amplitude, right? For this case, it was, 14 millivolts was how much I was wiggling it. So if I want to wiggle VBE, let me do what I did previously and sort of make a axis here, like this, right? So I'll have VBE, little VBE on this axis here, and say I'll wiggle it between this amplitude. So I have that amplitude going up there. I'm going to take that amplitude here, bring it up there. And so that's where I'm wiggling my VBE right there. And this is time. That's VBE versus time on that axis, right? So if I wiggle VBE like that, and this really should be a straight line, so I guess I'm trying to make that a straight line. What's going to happen is I'm going to intersect this curve, and that's going to tell me what IC is doing there. But okay, that's not actually what I'm doing here. What I'm doing with my small signal analysis is I'm approximating this curve by a straight line. Right? That's where my Taylor series expansion comes in. I'm not actually looking at the actual curve, which has some curvature. I'm sticking in a straight line that is the tangent at that point. Right? And so this curve right here has a slope equal to what we derived of as GM. Okay? That is the transfer function we're using in small signal analysis. So where this blue thing intersects the green is going to tell me how much current, so that comes up, it's intersecting right there. It's going to tell me how much current I have on the small side, and then on the top side, where it intersects the green, tells me where the current is up here. Right? So my current in this case, after coming out of this, I mean, obviously I didn't do a good job of this because these should be equally spaced here. So how am I going to fix that? I'm not sure how I'm going to fix that. I'm going to pull this down a little bit here at the bottom. Yeah, I guess that's the best I can do. let me pull this down here. These should be the same distance. That distance and that should be the same distance. Okay? So I'll pull this across there. I'll pull this across here. And that then is what my collector current looks like coming out of this. Okay? So that's the output current, but what we're really getting out of this is an output voltage, right? It's not an output current. So now I got to go on this axis here and look at that change in collector current. And so again, on this, I have to find my bias point, and maybe my bias point's right here. I don't have to find it. It's where the load line intersects the line for the transistor here. And this line for the transistor, this is for one case. This is for the bias point of the transistor. So I should point at this and say that's for VBE, this large signal VBE right there. Okay? And so from that, I can go ahead and project down and across. Across is going to give me my collector current I sub C. Okay, the bias point for my collector current. Down is going to give me my DC bias voltage, capital V, capital CE. Okay, and then around here, I'm going to do exactly the same thing that I was doing before. I'm going to wiggle, this time IC, because VBE, right, wiggled IC. And so IC is wiggling here. Maybe I'll show it like that. And then coming down like that. And so in actuality, IC wiggles like this, and that causes a wiggle in VCE as well. But actually, I'm not doing this right, so let me fix this a bit. This is not entirely correct. Because what I have to do is I have to put in the VBE curves that correspond to this excursion in VBE. So if this excursion in VBE is going from this VBE to a plus little VBE to a minus little VBE here, then the curves that I'm really working with are these. I guess I'm still green here. So I'm going to come up here, and I'm going to have another curve like that. And then up here I'm going to have another curve that's going up like this. And this curve up here is for VBE, the large signal VBE plus little VBE. Okay, and this curve down here is for that same DC bias VBE minus little VBE. Okay, so I have those two curves, and so to really do this correctly, I have to get the intersection point here for these curves, which I guess ends up being close to what I had before. Exactly what I had before, pretty much. So this comes down, and then my actual output signal here, which will be my little VCE, what I'm taking as my output, then I can project here. And that becomes my VCE here, where this is time as well at the bottom here. Okay, so if you want to look at this physically, what's really happening, you know, I'm wiggling my VBE, that's causing a change in I sub C, and that change in I sub C and wiggling in VBE is causing these curves to move, that I sub C is moving as well across this, and so where that load line intersects this transistor is moving basically. So the intersection point of the load line with the transistor moves, and that's what creates my output here. Okay? Kind of a complicated thing, and so hopefully you understood that as I went through it, but if not, I guess you can go back and watch this lecture again just to get all of it. Yes?
So, look at the top chart. VBE changes, which changes IC. Now, the dependence on VCE changing.
Yeah.
Is it on IC or is it dependent on VBE?
It's dependent on both, basically, because I've got IC and VCE on that. It's dependent on everything. And so it's really more the VBE that's moving this thing here against a linear plot. So I will say it's dependent more on this resistor RC and that VBE.
That kind of constrains the current.
Yeah, so the RC keeps it very linear up here, right? Because the RC is linear, it keeps that output sort of linear. You can also see that I'm biasing this in a point where the transistor also looks very linear. So as VCE is changing, that's why I can have a very large variation in VCE. Right? My variation in VBE has to be very small. And I guess I drew it large here. That's where I ran into trouble at this point here. But if the VBE variation is very small, then that Taylor series expansion works. But even if the VCE variation is very large, I'm still okay because this looks like a straight line out here on the transistor. Okay, so the output can vary a lot, but the input cannot very much. And so if you had to give a rule of thumb for the input, how small should the input be in order for you to stay linear? If you had to give a rule of thumb for that. 10 what?
10?
Oh, 1/10? Yeah, that's not a bad rule of thumb. But a better rule of thumb you can make by just writing out the IC equation. Right? So IC, let me do the total IC. Remember that was IS times E to the what? The VBE divided by VT. So an exponential of VBE divided by VT, if I wanted to make sure that this was small signal, I would make sure that VBE was less than VT. Significantly less than VT. So I would say just from this, for small signal, I want VBE to be less than VT. Right? Remember VT was 25 millivolts. Okay? If I do that, then my small signal analysis is probably going to work very nicely. And most of the time, that's how small that input's going to be. It's actually going to be much smaller than that in most cases. Okay? Any other questions about this whole thing? Okay, so let go ahead.
Really quick, if VBE was like even like a third or a fifth, if it was a fifth here of VT, wouldn't that be like 1% of the IS?
Yeah, it would start bringing you closer to the nonlinear region. But you know, I'm even okay with it being 10 millivolts or something like that, or even 20 millivolts or something. I mean, my example was 14 millivolts already, right? But in most cases, it'll be much smaller than that, because we're really trying to amplify extremely small signals. Okay? All right, so let's go through and do another thing here. And you know, you went through this whole thing, and this was a lot of work. Okay? It shouldn't be. So the way that you should be thinking about these problems, and you don't need to do it now, okay, but I just want to illustrate to you how you will be doing these problems in the future. Okay, you would be faced with this problem. So you're given this problem right away. Same problem. Okay, but instead of replacing this transistor with its small signal circuit, you'll replace nothing. You'll look at this transistor, and when you look at this transistor, what are you going to see? You should be able to see the small signal model right on this transistor. Because looking into this thing, I really have an R-pi resistance right there. Right? And I know that my VBE is right across that R-pi resistor. Looking across the collector to emitter of this thing, what do I see? I really have an R0 across that. I also have a controlled source coming across that. So I know that my collector current going through this, I sub C, that's going to be GM times VBE. Okay? If you can look at that device and see what I'm just showing right here, you can do things a lot faster. And so let me go ahead and do this problem again, but looking at the device by the R-pi and R0, and that GM times VB is going to come into play at a certain point too. So this is a simple problem that I'm showing here. But the way that I would really do this problem is I would say, okay, I want the gain from Vs to V0. So I can write that as V0 over Vs. But now I can write that as multiple gains here. I have a gain from Vs to this node here, which I'll call 1. So that gain is going to be V1 over Vs. And I'm going to multiply that by V0 over V1. So I have those two gains cascaded there. And all I'm going to do is multiply those two gains, but when I calculate these gains, I have to make sure that when I go from Vs to V1, that I'm accounting for loading by the next stage. And so Vs to V1 is going to these resistors, but the next stage is this transistor. I've got that R-pi loading this thing. And so at this point, I can say that if I look in this direction here, if I look in that direction there, and let me move this a little bit below to give myself some space. Wow. Uh-oh. Okay, possibly I cannot move that down to give myself some space. So I'll draw this somewhere else. So it's already on top of that 1 there. Let me move that 1 so that it's a little okay. It's not giving me an eraser right now. All right, so don't worry, I'll finish this now. Okay, so if I'm looking at the resistance scene looking this way, those are 2 arrows looking in that way, then that resistance scene looking that way is this R pi going to ground, in parallel with R1 also going to ground, and R2 going to ground. Everything going from that node to ground is in parallel, whether I'm showing it going up or down. So that resistance looking in that way I can call Ri. That's just R pi parallel with R1, parallel with R2. That's making a voltage divider with Rs. And so I can just write immediately here, this first gain is just going to be that R pi parallel with R1, parallel with R2, divided by R pi parallel with R1, parallel with R2, times the gain of this next stage. And if I have this committed to memory, I know that that's minus GM times R naught parallel with RC and parallel with R1, sorry, with RL. Okay, and then right away I've written down that gain. You notice how I've done that? I did it because I've memorized that the gain from the base to the collector is minus GM times whatever resistance I have hanging out there. That's what you'll be doing in the future. You will not be drawing out the small signal circuit. You'll just have that memorized with this thing. Think about it. When you do circuits with resistors, inductors, and capacitors, are you drawing some special circuit for the inductor and the capacitor? You're not. You know what an inductor and capacitor does. That's what I want you to be able to do with the transistor. I want you to be able to know what the transistor does. Look at it as the transistor, not as some combination of resistors and a controlled source, but as the transistor itself. If you could do that, you could solve this problem extremely fast, which I just did right here. Okay, and I did that because I committed some equations to memory. How many equations do you have to memorize to do this? I count 6. Later on you might claim more, but it's really fundamentally 6 equations. If you can get 6 equations in your head, you'll be able to do with what I just did, but with circuits with 10, 20 transistors. Okay, which is where I want you to get. Okay, so this is your first inkling of inspection analysis, but let me just say we'll do more of this later. Okay, and so that's it. I think, yeah, we're out of time. That's it for the class today. So I'll see you next time.